Good evening, everybody. Welcome to the continuation of our series into the simplified modeling process for biodiesel production using model, trialine, very straightforward alcohol, right? Methanol and trialine. Simple process, right? Now, previously we had shown that you could actually utilize, in this particular case, the R stoit and the RCSTR reactors, right? We had described or defined the specifications for each of the reactor types, explain the utilizations or the uses for each reactor type, right, as a basis for, in this case, predictive estimation of the yield, and in this case, non-predictive estimation, where you have an idea of the stoichiometry and the conversions of the reactor, right? Now, the next thing we need to do is to check out the results, right? So you check out the results. You just right click and click on the results tab. First, it's immediately obvious that you have a high temperature product and a high pressure product, right? Which is a consequence of the reaction conditions imposed at the start of the simulation, right? It's also obvious at this stage that you have about 800,533 kilograms per hour methyl oleate produced from the system. Methyl oleate in this case is our FAME, fatty acid methyl ester, which for all terms are in all cases, for this case, is more or less biodiesel, right? And you have a significant amount of unreacted trialine, right? And you also have a significant amount of methanol, which is not unexpected, given that we added we had to maintain a 42:1 molar ratio of methanol to trialine to achieve convergence, right? Now we have quite a lot of trialine here, okay? Now one way, we need to find a way to increase the conversion of trialine without tampering with the conversion specified in the reactor model, right? So one way I typically suggest for such a reactor system is to just introduce a kind of purge where you can take part of the stream back into the reactor, right, to increase the net yield. Alternatively, you introduce another reactor, but this will have implications on the capex the capital cost estimates of the system, right? So in this case, we might introduce just a splits. We can call this SP, right? You connect the stream to the split, right? Introduce streams. Let's call this just stream 1, just for simplicity. We don't keep writing names, right? Then you bring out the split stream that you are trying to recycle, so we can call this recycle 1, right? You just need to connect it to destination, so you connect it to your destination, which is back to the reactor, right? And we just need to define what the split is, right? We can assume that we're recycling half, because it's mass basis, right? So we're recycling half of the product back into the system, right, to see if we can enhance the conversions. We initialize, and we are told that we have all the required inputs in this for this particular model to converge, and we run the simulation and see what we get, right? Yeah, it's completed. You come here, you check if there's an improvement. Let's see if the level of improvements, if there is any, of this so-called purge approach. So you see here that now, yes, before it was about 800,533, now it's 842,666, right? For the fatty acid methyl ester, the biodiesel yield, right? So this is one way to increase the yield of the trialine without necessarily having to introduce a reactor and without having to alter the conversions that we had previously specified, right? Yeah, so now the next thing we observed when in the tab I just opened up was that the exit stream had a high temperature and a high pressure, right? high temperature and a high pressure, which is a consequence of the conditions that we impose in the reactor. It is our storage reactor, R1, right? So 280 degrees Celsius and 28 megapar or 280 bar, right? So what we need to do, assuming this was an industrial process, which is what we're trying to mimic, right? You introduce a pressure changer, right? So I'm introducing a valve, right? So we can call it V1, right? We introduce a valve. We now reconnect to the valve, so we reconnect to the destination, which is our valve, right? Introduce the stream from the valve, right? So let's call this stream 2. Yep. So you now specify the conditions for the valve, right? So all you really need to do here is just to specify the outlet pressure. So I stick to the atmospheric condition of 1 atmosphere, right? And you see that it's specified, it's now changed to input changed. You reinitialize, it tells you that you have specified all the input components, required input complete, right? Then you may choose to run the simulation there and then, right? And I'm running it again. Typically what I do is I just keep developing the model, but just so that we see that it's converging, so we can follow what I'm doing, right? So now we have reduced the pressure to atmospheric pressure, but the temperature of the stream is still high, right? Of course, based on cooling effects of rapid expansion, you expect the temperature to drop slightly, right? This is basic chemistry, right? So yeah, so the next thing we need to do is to find ways to cool this stream further. So we may introduce a cooler, right? So we can call this a cooler. Reconnect the stream to the cooler. So you connect to destination, right? Introduce a stream exiting the cooler. So we can call this stream 3, right? And specify the conditions that this cooling will take place. So I'm saying it's cooling to 25 degrees and the pressure is maintained at 1 atmosphere, right? And that's that, right? Right, so typically again, this is unnecessary. You don't need to be reinitializing. I'm just doing this so that we can all follow what's going on. So we reinitialize, run the simulation, it converges as it should because it's very simple. We just added just one particular model unit, and you have it converged. Now you look at this stream. Now the target is to extract the methyl oleate, right? So the fatty acid methyl ester from the mix. So you have within it, you have significant amount of methanol, you have some reacted triolane, you have your methyl oleate, and of course you have glycerol, which is the byproduct of the reaction of the transesterification reaction, right? So what we do, we can just, given the amount of methanol produced, and also recognizing that methanol has significantly different boiling temperatures compared to the other components of methyl oleate, triolane, and glycerol, quite lower actually. We can just employ a very simplified vaporization step, right? So we can use a very simplified flash vaporization step, excuse me, which we call, you can just call it VAP1. Again, you call it whatever name you want, it's entirely subjective, but provided you use names and icons that people can understand. So you reconnect to destination, which is to the flash vaporizer. So okay, before I do this, I want to spread this a bit so that we can see it clearly, right? We now introduce the top stream, which should be largely the methanol, so we can just call methanol, and we introduce a bottom stream, which will be everything else, so we can call it residue, right? So now to facilitate this vaporization, we need to introduce some form of heating. Now we have already cooled this stream, so we need to make use of the heat that is generated from such a cooling operation, right? So what I do is just to take, we take the heat stream from the cooler and we connect it to the flash vaporizer, right? And call it Q1, to the vaporizer, right? Now this is quite simple. All I did was just to come here. You can specify this nature of the stream you're using. So a mass stream, a material stream, heat stream, work stream, right? So I clicked on the heat stream, clicked on the particular units, the particular unit I'm concerned about, and linked the units to the target units, right? If that makes, if that's clear, I hope you understand, right? So I clicked on it, linked it directly to the vaporizer, right? So that all the heat that was recovered from here can aid me in the vaporization process without me needing to supply some heat by specifying the temperature, right? So I haven't done that. You come here, you need to specify what pressure this is happening, right? With valid phase of vapor liquid, because some will be vaporized while there will still be some liquid, given the differences in boiling temperatures, right? Now we can use to suppress the evaporation of unwanted products. I tend to typically slightly increase the pressure of during the flash vaporization process, right? Just to suppress possible vaporization of other components that are not methanol, right? So I can just use 2 atmospheres here for simplicity, right? Reinitialize, input required complete, right? And we run the simulation, right? Quite simple. So we have now been able to recover most of the methanol. I assume we should have recovered most of the methanol, right? You see, most of the methanol is with very little. You need to suppress. See, they still have some, so we may need to increase the pressure a bit further. You see what I mean? So you need to suppress the generation of all these useful products, So what I could do is to go back here and increase this to 5 atmospheres. Right? Of course, you should also realize that this has implications to the costing, because the higher pressure you impose, the higher the cost of the equipment, because you require higher quality fabrication materials, right? So this will have implications when you do the costing, right? So we'll come back here and see what the difference is. We can just check the mass fractions. So we still have some a little amount of trialing, but we still have some methyl oleates, which is our biodiesel in the stream, right? So again, I may choose to increase it further, or I may just choose to leave it that way to move on. But let's just increase it further and see what we get, if this will significantly improve, right, the recovery of the methanol without impeding or without any associated methyl oleate in the stream, right? So yeah, so we can check this out. So it's not perfect, but still it's a bit lower now, right? You have low glycerol, low methyl oleates, right? You have lightly methanol in the stream, right? Now, of course, what you could also do, right, having given that you still have some useful methyl oleates in this distillates, or not distillate really, but in the vapor phase, is to further increase the pressure, right? So these are design specifications, and a design that based on your own design preference, right? For now, I think this is fine, right? So we've had specified it to about 10 atmospheres, with about 88% of the vapor phase being our target methanol, right? Now you have a residue that is largely composed of the trialine, unreacted trialine, glycerol, and of course the target biodiesel, right? So in this case we have largely the methyl oleates, which is the largest component of the stream, right? But we need to get rid of every other thing to get our target product, because that's the purpose of this modeling. We need to get biodiesel, right? In other words, our fatty acid methyl ester. That's what we need to get, right? So based on this statement here, that you have components with very varying boiling points, boiling temperatures, right? It is immediately clear that we could utilize a distillation column to more or less separate these components while maintaining the target component, or getting our target component of methyl oleate from the mixture. Now typically, based on these temperature distributions, it should be immediately clear that for our system, the distillates will be composed largely of residual methanol and glycerol, while the bottoms of the column will be composed mainly of the unreacted trialine and the methyl oleate, right? So now we come to where the columns are, right? Recall we have several kinds of columns varying with degree of accuracy, right? You see, some columns are more rigorous than others, right? As an illustration, just as I did previously where I used a duplicator, I'm going to introduce another duplicator just to demonstrate what I mean by level of accuracy, or the rigorous level, or the level of the rigorous reactions undertaken, right? So let's just call this duplicator 2, right? So I'm trying to duplicate the stream just the same way I duplicated the stream earlier on. So reconnect to destination, right? We introduce our material streams. So we have one stream here. We can call this stream 4. Introduce another stream. Call this stream 5, right? Now the first column we're dealing with is the DSTW. It's based on the Frings-Underwood Gilligan modeling approach, right? Gilliland method, right? So it's an approximate approach. So I'm sure in our 300 level, I think for most chemical engineers, their thoughts, distillation columns and all that, the 300, 200 level. So I expect that we have an understanding of the approximate Frings method, right? The Frings-Underwood Gilliland method, right? So essentially you use a Frings relation to get the number of stages and all that. So this can be found in very basic chemical engineering texts, right? So we're going to try that out first, right? And you can call this column 1, right? Then we'll try the Radfrac model, which is the more rigorous column based on more rigorous correlations, right? So we'll call this column 2, right? Now typically when I'm dealing with distillation column, because I have no knowledge or no idea of what the preferred number of stages will be, I have no knowledge of what the preferred feed stream layer, like tray, will be, like the tray where the feed is supplied to the column. I have no knowledge of this. So I typically first introduce this approximate column that tells me the number of steps or the number of trays required, right, in the column, right? It tells me some useful information regarding perhaps the duty you know, the heating duty required by the reboiler, the cooling duty required, you know, and all that, right? So it's quite important that you get familiar with both the approximate and the rigorous methods, right? So okay, let's go on. Let's talk less and move forward. So what we can do now is to click on the column. Now you see all you need to do is to specify the number of stages, which you do not know, right? But we can have an initial guess of say 10. I feel 10 just seems like a cool number, right? Now this is the light components, which is methanol, and we're assuming we're targeting very high recoveries, right? And in this case, this is the heavy component in the distillate stream, right? Of course, we do not expect, we call this a heavy component, which is the material unit. We expect very, very little. That's what we're hoping for. So we can call it 0.001. Very little of this in the stream. And we can specify column, it's operating in pressures of operating at pressures of 1 atmosphere, right? Now once you have done that, you have specified, very simple, and you see that the C1, which is our column 1, is now fully specified, right? We just reconnect this to the destination, right? Now I think I will need to remove this column so that we can just focus on this approximate one, because I don't want to fill up this without getting the values for this, right? So let's get rid of this. We can delete this column. So this is the rigorous one, the rigorous column. Delete this just to make sure that we are able to move forward, right? Okay, so now we introduce our streams, right? Now I introduce our stream. We can call this stream 5. Oh, it already exists. Let's say stream 6. I call this stream 7, right? Call this stream 7, right? We reinitialize, right? And we run the system or the simulation to get the necessary values, right? We expect convergence because again this is a very simple model. And what you now do, you come here, right? Check the results. You see, now you have information that you need. So when you are now dealing with the rigorous model, the RAD-FRAC model, you can utilize this as your initial guesses. So you have your number of stages, right? You have your reflux ratio, right? You have your feed step, right? You have your duties, your condenser and your cooling, and your reboiler duties. So this is quite useful. It is quite useful to be able to utilize the approximate method first, right? Prior to utilizing the rigorous distillation columns, that is RAD-FRAC. So in your own simulations, you may choose to introduce this duplicate stream and introduce like a dummy stream, right? Prior to modeling your actual distillation column.